Good morning, afternoon, and evening, everyone. When this was organized, Ed Ripley had contacted me and asked if I would do an overview on the Midcontinent Rift in the Lake Superior region, and was happy to do that. It's quite a large topic, as you can imagine, so I'm going to shoehorn this into less than 15 minutes, which will be a challenge, but this will be the very abbreviated version. The Midcontinent Rift is basically a well-known large igneous province now, but its early manifestations were actually recognized by the enormous gravity anomaly that runs through the middle of North America from the Lake Superior region down to as far as Oklahoma, and then underneath lower Michigan. This arcuate structure, which is also recognized in its magnetic pattern, was known as the Midcontinent gravity high. And then with the advent of plate tectonic theory, it became recognized as a very large intercontinental rift. The exposed geology of the rift in the Lake Superior region is shown here. There are basically two major components, the igneous and the sedimentary. The igneous components are composed of a series of flood basalts that mantle the margins of the lake. On the North Shore of Minnesota, it's called the North Shore Volcanic Group, the Portage Lake Volcanics on the backbone of the Keweenaw Peninsula and Isle Royal, the Osler Volcanic Group, Mamant's Point at the east end, Michipicoten Island, and so on. Early on, without good age dating, the only way to really correlate these volcanic packages around the lake was by the recognition of a profound magnetic polarity reversal, going from lower reverse polarity lavas to magnetically normal lavas in the upper sequences. Immense amounts of intrusive rocks, the largest being the Duluth complex here shown in the lighter brown, second largest gabbro complex on Earth after the Bushveld. Then there are more hypabyssal intrusions. This is the Beaver Bay complex in Minnesota, the Nipigon sills around Lake Nipigon, the Mellon complex down here at the Wisconsin-Minnesota border. And again, just to orient everyone, here's Marquette, where we would have had the meeting, the town of Duluth, and Thunder Bay, which is where I am situated right now. Some of the more intriguing intrusions actually are some of the smallest ones, and these are outlined here with these yellow stars. They're ultramafic intrusions. The most famous, which we'll hear about today, is the Eagle outside of Marquette, but other things such as Tamarack in Minnesota, a whole slew of them just north of Thunder Bay, are prospective for copper, nickel, and PGEs. And then there are sediments that kind of overlaid the volcanic rocks and then were later thrust up into them. And that really highlights the structural complexities of the rift. I'm sorry, let me go back. You can see that the tilt of the flows around the rift generally define a trough, a syncline. It was called the Lake Superior syncline before the Midcontinent Rift was understood. But it's cut by many faults which now have a normal displacement, but originally started out as normal graben-bounding faults. Seismic profiles that are cut through the lake that were done in the late 80s, part of the GLIMPCE program. This is line A, and just to show you what that looks like across the center of the rift, you can see this is the Keweenaw Fault on the right, the Isle Royal Fault on the left, and the lavas of the Portage Lake Volcanics and the Osler Volcanics occupy almost half the crustal thickness bounded between these two ridgely graben faults, with now reverse motion on them. And you can see there's very little lavas extending outboard of that graben. The other interesting thing to note in this geophysical model is the presence of a very large underplated region that actually explains a lot of how the rift evolved. Putting all these packages together, just the lithostratigraphy of the different packages, now we have very high precision uranium lead age dates that allow us to correlate all these volcanic packages and the intrusive rocks across the rift. I'm not going to go into a great amount of detail, but with all of this correlation that's possible, we have identified four and maybe five basic magmatic stages of the rift. And that's what I'm going to focus on for most of the rest of my talk here. I should mention, these are all ages that were done under 207, 206 calculations. A new series of ages collected by Nick Swanson-Heisel out of UC Berkeley has been arguing that we should be using 206, 238 ages, more precise and more well-behaved. And you can see the changes of the same rock types create a significant younging of the ages of these sequences. For example, the Duluth complex, all these ages of the Duluth complex, 207, 206 ages, are about 3 million years younger when calculated with 206, 238. Same with the Beaver Bay, and you can see all through here, generally 2 to 4 million year younging ages. So we have to make sense of this at some point and be able to correlate these different styles of ages. Moving into more of once we can correlate these packages, looking at the chemostratigraphy through the rift, through the volcanic packages, there's a few things worth noting that, again, help highlight these different stages that we identify. The early stages down here, they start out, this is the Mg number range in the lava flows. This is the epsilon neodymium values. You can see early volcanics come in very primitive and uncontaminated, but very quickly show signatures of contamination and epsilon, as well as thorium increases relative to rare earths. And so we move into this very contaminated and evolved stage at the end of the early stage. And then the mafic magmatism shuts down for about 4 million years. When it reemerges in the main stage, it's still evolved, but it's uncontaminated. And so that the tectonic model really has to account for this. When you look at the felsic rocks, they start to show themselves again at the beginning where you start to see signs of contamination. They are the only lavas that we see in this hiatus period. Here it's called the latent stage. But then, and when you look at the epsilon neodymium, they get progressively negative as you go up. This is suggesting that these are partial melts of the crust. We're melting progressively older parts of the crust, going from maybe early Proterozoic anatectic melts down here to Archean melts up here. So we kind of put all this together, and just going through kind of stages of the model, I'm employing the idea that we have a starting mantle plume. Given the volume of magmatism that we see in the Lake Superior region in particular, this all seems to make sense with a very overheated mantle, and a plume model has been invoked by most people. However, I'll mention that that's sort of beginning to change. The earliest ages that we get are about 1115. However, these are mainly ultramafic intrusions. Some of them show some mineralization that's being explored for. However, there's been some redating done, and these may not actually be as old as it suggests. So if these are indeed, we don't see any volcanics of this age, that we know. The volcanics don't start until about 1109. But it suggested that perhaps there was a bulging of the crust, a crustal flexure, and any eruptions that could have happened might have been eroded away and not really preserved for much of the rift. The main early stage is where we see a good representation in the volcanic pile. We start out early with primitive lavas, as I say, coming pretty much straight out of the mantle. But then we're starting to see evidence of interaction with the crust and the sublithospheric mantle, and the beginnings of the underplate, partial melting of the lower crust, creating felsic magmas that are intruded into the Duluth complex, as well as erupting as rhyolite flows. So this is and we also get most of the copper nickel PGE enriched ultramafic intrusions are of this stage, this early stage. Then we move into this hiatus or latent magmatic stage. And this is, I've been proposing that, in fact, this is where we build the most of the underplate. And the reason we don't see mafic magmatism is because we have sequestered them into the lower crust and created a density barrier by severe extensive anatectic melting of the lower crust. This is also where we generate anorthosites, the famous anorthosites of the Duluth complex that have been that you see along the North Shore. So this is, I think, created by flotation of plagioclase in these lower subcrustal chambers, and then they're brought up later during the main stage. So this latent stage is the inflation period of this lower crust. Then the main stage is when we basically evacuate this lower crustal magma chamber. We've density clarified the crust. Kent Cox had that great term for what happens to allow underplated magmas to erupt in blood basalt provinces. But this is the main graben forming stage and eruption. The Duluth complex, the main part of the Duluth complex is injected at this stage, and great outpouring of volcanics and intrusions at this stage. The plume, if there is a single-headed plume, starting plume here, it's basically waning and perhaps detached from its tail, and I'll give some evidence why that might be the case. And then finally, we get the thermal collapse of the plume and subsidence of the graben and infilling with sediments that we see now flanking and topping over the volcanics. And then finally, rather than going to opening as a complete intercontinental rift, it has basically inverted with the development of a horst, and this is thought to be caused by the collision of Amazonia with Laurentia at this time at 1.1 billion years ago to create the Grenville orogeny. So that's kind of the tectonic stages. Recent work by Nick Swanson-Heisel has really given us a new insight into the evolution of the rift. And the paleomagnetism that he's done with very high precision age dating shows that Laurentia pretty much traveled 30 degrees of latitude in the period of magmatic activity, a 25 to 30 million year period. So this thing was really clipping along at a rate of over 20 centimeters a year. And what was happening was Laurentia up here, initially up by the northern hemisphere, was drifting to the south, and there was a convergent margin against Amazonia, and a very strong slab pull was pulling it southward and ultimately colliding with Amazonia and other Baltica and so on to create Rodinia. So it's thought that perhaps the rift is really a tear by the pull caused by the subduction at the forefront of the Laurentian plate underneath Amazonia. So this is an intriguing idea that we have to take into account. And if there was a single plume, that it was, again, North Laurentia was traveling very quickly over that plume. So
1 minute.
Thank you. I'm almost done. Great. So I think we have to consider other ideas that we definitely have a high degree of partial melting of the mantle and giving rise to great thicknesses of magmatic products. However, this may be due to the overheating of the mantle as Rodinia is being assembled. Ideas of subduction zones are causing upwelling in other areas that may come up underneath the rift. And so it's not really a single plume model as simply an overheated mantle idea. Just very briefly, I know this is all about mineral deposits, but we're going to be hearing all about Eagle in a moment. The mineral deposits in the Lake Superior region, the most famous are the native copper deposits along the Keweenaw Rift, which infill the pore spaces of lava flows and interflow sediments. That's what it's well known for, but the magmatic deposits around the rift pretty much touch all bases as far as deposit types that Tony was well aware of and commonly would cite it in his papers. Just ending it here, the copper Ni-Cu-PGE intrusions that we're going to hear about Eagle, and we'll see reference to Tamarack and the basal Duluth complex and so on up in Ontario, provide a whole host of interesting and attractive targets that hopefully will, besides Eagle, yield some productive mine sites. So I'll leave it there. Thank you.